There are few things in this world that are more dangerous than trawling eBay at midnight. That's how you end up with a laboratory microscope on your desk for, surprisingly, only about $200. This is a Nikon Labophot. I have no idea how you're supposed to pronounce it, but it's a really nice laboratory microscope from the mid-1980s. And most importantly, this one is trinocular, which means you can bolt a camera to the top of it. Now, this one didn't come with a camera, so we're gonna have to figure out something about that. And also, this one was primarily meant for biology. That's why you have a light on the bottom to shine through whatever specimen you're looking at. And I don't want to do biology with it. I want to do computer science and electrical engineering. So we're going to have to figure out some way to illuminate things from the top side, because a lot of the things that I want to look at, light won't pass through. But if we can figure that out, we can do something that I've wanted to do for a very long time, and that's look at firsthand the silicon dies of integrated circuits. But before we get into any of that, we got to clean this thing up because it is filthy. To get this thing clean, we're gonna have to tear it down. The trinocular optic in particular has been sitting face up with no cover on it for who knows how many years. The eyepieces have also never had a cover on them, it appears, but they just pull straight out. Then to get the entire head off, we just need to loosen up the thumb screw and the whole thing pulls free. There were 4 objectives on the scope already, a 4x, 10x, 20x, and 40x. Interestingly, I think these are phase contrast objectives meant to be used with a condenser to create a nice highlight around the edges of the specimen. At any rate, actually, I'm gonna go on a bit of a tangent here for a second. This week's video nearly didn't happen. Square Enix was running a sale on Steam and I finally broke down and bought Final Fantasy VII Remake and Rebirth. I played the original Final Fantasy VII when it was new back in 1997 and loved it. And I know the remake has caught a bit of hate, but man alive, so far I absolutely love it. It's just different enough to feel like a new game, but so far it's following the story close enough that it still feels like Final Fantasy VII. It's been a massive amount of fun, but also it's consumed way too much of my week, and now I'm on the back foot to get this video edited up. Looks like past me has the microscope torn down. Back to work. That came apart way easier than I was expecting, and it's a good thing I decided to take it apart because a lot of the optics are very gross, particularly the trinocular optic. That thing is just filthy. But also the power supply on the bottom for the light is way more complex than I was expecting, and it didn't handle shipping very well. The bulb is all the way at the back here, and it passes through a diffusion lens, then into a collimator, I believe, before hitting an adjustable iris right here, then a mirror to steer it up, where it'll ultimately pass through the specimen and into your eyes via the optics. Now, what surprised me about this was that that bulb is actually being powered by DC. So your AC comes in through the cord here, passes all the way around to the main transformer here. This takes the 120 volt AC and drops it to 9 volt AC. That then goes into a full bridge rectifier to turn it into DC before coming over to this pass transistor here. Now this pass transistor is controlled via this main rotating knob up here that goes between 1 and 6. It also has a power switch to turn the whole thing on and off. But I'm guessing that this means that 1 volt is making it to the bulb, all the way up to 6 volts is making it to the bulb. And all this rheostat is doing is controlling how much energy is allowed to pass through this pass transistor here. Really wild to me that they would do it with DC, but also that they're not smoothing that DC. There's no capacitors anywhere in here. However, the bigger problem here is that the transformer here broke loose in shipping. The tie-down straps that are supposed to hold it down ripped out of their spots, and this whole thing is loose. That's a disaster waiting to happen, so we need to fix that. The first step is to get the remains of the mounts out. Interestingly, the screws don't look bent, though the metal tabs most certainly are. The problem is the screws are too short. If the metal tab is flat, the screw can only engage for 1 or 2 threads. My solution was just to use a spring over the top of the transformer. This really let me cinch the screws down, engaging them properly. There's a little movement to the transformer, but that's plenty stable. Next, I'll use some canned air to get all the cobwebs and dust out of here. I don't want to use anything that might deposit oil on the mirror or lenses.
And after getting it back together, let's give it a little test. Yep, the pass transistor seems to be working just fine, as does the adjustable iris. All the painted surfaces of the microscope are a little dingy, so they'll get a wipe down with a shop towel soaked in Simple Green. The adjustment knobs were also quite gross, with years of grimy fingers touching them. Simple Green and a toothbrush made a massive difference on them. The sample holder plate will also get a full wipe down. Who knows what's been spilled on here over the years. After getting the sample plate back in place, it's time to clean the optics. And the best cleaning agent for precision optics is ethanol, or Everclear. Now, I don't have the appropriate wipes, but I do have these chamois swabs used for cleaning hard drive platters. First, I used a syringe to flush the optic as best as possible, trying to get all the big chunks of dust washed out. Then I would soak one of the chamois swabs in Everclear and very lightly clean the optic. I would then use a dry chamois swab to wipe the optic fully clean and finally hit it with canned air to get the rest of the moisture fully out. I repeated this process for all the optics except for the objectives themselves. It may not be the proper way that you're supposed to clean these, but it certainly got the job done and is a far cry better than the lackluster way in which the thing seems to have been treated before I got my hands on it. And now that all the optics look crystal clean and the whole thing doesn't feel gross to touch, let's get it all back together.
A little bit of Everclear solves all problems, at least in terms of cleaning things, and certainly don't drink the stuff. That is straight poison, but it works absolute wonders for cleaning this thing up because the microscope came out looking amazing and the optics are all crystal clear now. So all we got to do is get a light somehow attached to it so that we can illuminate things from above, and we got to figure out how to mount that camera up on top. And for the light, I bought this thing. It was like $12. It was super cheap. Has 3 AA's in the base with a nice magnet on it, and then it's all flexy, and you can turn it on to shine. Well, that's really bright. So I think if we could find some way to mount this behind it, then I can steer the light around the back of the microscope and shine that on whatever it is that we're looking at. And in order to make that mount, I think all I got to do is just bend up a little piece of steel and bolt it to the back.
I think I'm missing something on the back because there are 2 little holes right around this opening, but I can make use of these little holes to mount a piece of steel for the flexible light to stick to. I dug through our scrap steel box and found a nice piece that already had a bend in it. I just have to slice it to size. Then I'll take it over to the grinder and clean up the edges so I don't make a blood sacrifice, as well as round off the corners. I'll measure out where the holes of the microscope should line up, center punch them, and then drill them out easy peasy. And miraculously, I actually only had to cut once. This almost never happens to me. I'll just lock the whole thing in place with some nuts on the backside, put the whole thing back together, and bam! The flexible light sticks to the metal plate perfectly. Then I can just twist it around and aim it at whatever we're looking at with no problem whatsoever. Next up, the camera. This little generic Chinese microscope camera is what I'm going to be using. It does 1080p at 30 FPS, and it's nothing fancy, but should work for now. The only problem is, it was meant for a different microscope. It absolutely does not fit. So let's make it fit. The trinocular eyepiece is 31.4 millimeters, and the opening on the camera is just 24.3 millimeters. Let's pull all of the delicate internals out of the thing so I can work on it. After removing the 4 screws holding the sensor in place, it pulls up and out, but you gotta be careful about the ribbon cable. The sensor board itself can be removed by undoing 4 more little screws, and then yet again 4 more screws on the main processor board, and all the delicate stuff can be pulled out and set aside. Then I'll pop the aluminum case into the vise on our CNC mill and get to work. The first step is figuring out where center is. For this, I'll use this little edge finder. It has a spring-loaded conical tip that slips to the side. You just spin it up, move the axis in until it goes funky, then work it back until it's straight. Once I know where the edges are, I just divide by 2, move the spindle to that position, then zero it out on the computer. The outer diameter of the trinocular optic is 31.46 millimeters, so I'll make my cut with a diameter of 31.50 millimeters. To make the cut, I'm going to use conversational programming, essentially programming the steps the mill will take directly on the user interface. I'll do a quick test cut at a depth of just 0.5 millimeters, just to make sure I've got everything set up correctly. It's super cool to watch this thing cut perfect circles. A quick test fit of the optic, and yeah, that's perfect. Now I just need to update my conversational program to cut the full depth. The actual depth is 8.1 millimeters, so I'll cut to a depth of 8.0 millimeters in 0.5 millimeter intervals. I could definitely take bigger cuts, but I'm not in a hurry and I like to watch and make sure everything is going smooth. After it's fully cut, let's do a test fit with the optics, and man, that's flawless. Let's pop the optic back into the trinocular tube, then slide the camera on top, and now we're ready to set this thing up proper-like. The camera just needs a single USB cable to a computer, and that's it. This is an absolutely gorgeous setup now. The Microscope almost looks brand new despite being 40 years old. And being trinocular means I can record everything I see, which is just amazing. I'm extremely happy with how this thing turned out.
This little chip right here is what actually caused me to fall down this rabbit hole that we've fallen down today, because this is an MC68701 microcontroller. It has a full 68K instruction set on it, 2K of EEPROM, 128 bytes of RAM, a serial interface, 29 I/O lines, an internal clock, and a 3-function timer. This thing is essentially an entire computer on a single chip. The only limitation is that 128 bytes of RAM, but here's where the party piece is, because it can support external RAM as well, which means that you could slap a 64K SRAM next to it and essentially have a really formidable computer with just 2 ICs. That is absolutely wild. But the EEPROM that's on it, which is what you would load your microcontroller programs into, is UV erasable, which means that there's a little window on the front to erase that ROM. But it also means that we can look through that window and see the entire die of this IC without having to delit it or decap it or get chemicals involved to etch away some stuff. We can see absolutely everything through that window. The RAM, the ROM, the decoder, the ALU, all of it is visible, except that it's all so tiny that you need magnification to see it. But that's why we've got this microscope going on here. So let's slap this under the lens and see what we can see. I'm currently on the 4x objective, which when combined with my 10x eyepieces gives a 40 times magnification. Unfortunately, you guys can't look through the eyepieces. I've tried to line the camera up. It just doesn't work. But that's why we've got the trinocular with the camera sitting on top. However, the eyepiece for the trinocular setup thing is only 5x. So whereas I'm seeing a 40x magnification through here, you guys are going to be seeing a 20x magnification through the camera. However, you'll notice that on my laptop here, which is using the camera as a webcam, it's totally black. And that's because the way that this particular microscope is designed is that the light path doesn't go in both directions at the same time. It's only ever going to the eyepieces or to the trinocular camera. So what I have to do is take my eyepieces and rotate them to the left. And as I do that, you can see that on OBS here, we've actually got a little bit of a red image coming up, but it's totally blurred and out of focus. So I've got to shift the piece up, and we should see it start to come into focus here. And yeah, look at that. That is super cool. Now it is very red and also a lot darker. Now this little light here has 2 illumination levels, so I can switch it over to the brighter level. And I have no idea why it is so red shifted though. Through the eyepieces, it is like a bright, brilliant blue. So I have no idea where this red color is coming from. That has to be something unique to the camera itself. So thankfully, DaVinci Resolve has some pretty good color correction tools in it. I'm gonna try and color correct this to something that's much closer to what you're seeing through the eyepieces. But we can already see a whole lot of really interesting stuff going on. So I'll just move the workpiece around here and we'll see kind of how all of that's so cool. Look at that, we got up to the top here and we can see the bond wires that are going from the silicon die here out to the actual pins. We'll see if I can get that into a little better focus there. Yeah, there we go. That is super cool. And if we follow them around, we're getting over to the edge of that little circular window. So we're gonna have to kind of move down, and we can see there's more bond wires. And you can kind of, it's really tough to see, but you can kind of see the drivers next to the bond wires. Those are those big zigzag squiggly things that are going back and forth. That is essentially a very large transistor to create enough current to drive that pin that's going external to the thing. We'll just move it over this way here. Oh, we're working into the shadow here. All right, so that's a problem with having the light just only on one side. I'm gonna hit a shadow, but since it's flexible, I can take it and move it over to the other side. and look at that, now we're not in the shadow anymore. That flexible light is really, really awesome. If we move around here, we're seeing all sorts of neat stuff. Oh, that looks like we're in the big ROM array here. So you can see how it's just this huge swath of some stuff that looks absolutely identical. My guess is that that is the read-only memory, and when you shine a UV light on it to erase it, that's the part of the die that you're affecting. Let's move across. You can see those line drivers for the pins really clearly here. Look at that. You can really just see that squiggle next to one of those bond pads that's going out to the pin. Man, that's so cool. Oh, look, we got a number. All right, so C84N08-1. And I don't think that's text or anything above that. I think those are actually maybe test pads. And right above that text is a section of the circuit that is quite complex looking. That's clearly not ROM or RAM, that is pure logic. So let's zoom in on this. I'm gonna rotate my objectives out, go from the 4x objective to the 10x objective, which 10 times 5 should give 50x magnification for the camera on top here. So we'll just go ahead and rotate that. It's gonna hit my light a little bit here. Oh man, I knocked it loose. All right, we gotta come down a little bit here. And there we go, we're back into focus, but I accidentally hit the IC. Let's see if we can find the text and then work our way. Yeah, there's the text. So if we work our way back up from there, there's that huge confusing swath of logic. And look at that, you can actually see multiple layers of traces on the silicon die here. This is absolutely stunning. I have spent hours just looking at the beauty of the die of this IC, and that's just a single IC. I cannot believe that you can get a microscope of this quality for like $200. Like, that's absolutely ridiculous to me. Like, I spent like $70 on Italian food the other night. $200 for this is an incredible steal. I could not be happier with this late night eBay purchase of mine. And I mean, the things that we can look at now are limitless. Like, we could put so much cool stuff under here, but I do really want to look at more silicon dies. I want to delid a 74LS00 and pull out the absolutely minuscule silicon die on it and see if I can pick out where the individual NAND gates are and how they're constructed inside. I think it's going to be an absolute blast having this tool in the shop, and I think it's going to allow us to have a lot more really neat footage in upcoming projects. So I want to thank you all so much for hanging out with me today, and I hope to see you in the next one.